ladies and gentlemen. So we are about to begin Unit 5. Our first lesson is 5.1, which is on variation functions. So we have a warm-up to get us started today, and we want to graph the equation y equals 3x on the grid to the right. Now, don't overthink this. We have the equation y equals 3x. You can approach this in a couple of ways. You can think of it as, okay, this is a linear equation with a slope of 3, meaning I rise 3 and I run to the right 1 unit. The y-intercept on this is 0 because there's no value being added to that 3x term, right? So my very first point that I'm going to end up graphing here then is at 0, 0, meaning this graph, y equals 3x, goes through the origin. My slope is 3, so I'm going to go up 3 units into the right 1 unit because that slope would be like 3 over 1 if you're thinking of it in terms of rise over run. We need at least 2 points to be able to graph a line. If you want a couple more points, you could look at the slope going in the opposite direction, so going down 3 units and going back 1 unit. And then connecting these in a straight-ish line. Let's try this one more time. There we go. And we get the graph of the line y equals 3x. That's a pretty good warm-up, just getting us back into this motion of, how do we graph equations, and this one's linear, so hopefully that was a little bit easier of one for you to graph. Our objectives for today, we're going to graph direct variations, we're going to create direct variation equations, and then we're going to do the same thing for inverse variation. So what is direct variation? This is likely a new term to you, but it really is not that unfamiliar of a concept to you. So direct variation is a relationship between two variables, x and y, that can be written in the form of y equals some variable or some number k times our variable x. So y equals k times x, which is exactly the setup that we had for the equation in our warm-up, y equals 3x, where the y value equals 3 times that x variable. So there's a direct relationship between x and y. In this relationship, k is what's called the constant of variation. In other words, that's your slope. And you're dealing with a direct variation setup because you're going to notice this phrase in the instructions. Y varies directly as x. And sometimes these variables will be different, but it's important to note the sequence of this phrase. So it says y varies directly as x, meaning that y variable is going to be equal to whatever that constant of variation is times x. So let's put this to practice with looking at example 1. So we're given that y varies directly as x. So we are given that phrase, and I'm going to move my screen down here. There we go. So we are given this phrase of y varies directly as x. So that means we're dealing with something in the form of y equals k times x. We're told that y is equal to 27 when x is equal to 6. So we're given values of x and y, and we can use those to then solve for k, because we got to figure out what our slope is. So one way to approach this problem is we're going to say, y, which is 27, equals something, whatever k is, times our x value, which is 6. Solving for k, we're going to divide by 6. And we're going to get, if we reduce this down, 9 over 2 is equal to k. And I'm going to leave this as a fraction because this is my slope, and it's much easier to graph slope when it's a fraction than when it's a decimal. So my equation then in the end would be y equals 9/2 x. So that's my direct variation equation, or my direct variation function, and now I'm going to graph that. Just like the warm-up problem, it does cross through the origin at 0, 0 because there's no constant number being added to the 9/2 x. Now applying my slope, I'm going to go up 9 units into the right 2. If you wanted to do the negative version of that, you would go down 9 units and back 2. And connecting these, we get this linear equation graphed, or a direct variation equation graph. So let's take a look at example 2 where the variables are a little bit different and it's more of an applicable situation versus a graphing situation like in example 1. So we're told that the cost of an item in euros, E, varies directly as the cost of the item in dollars, D. So notice the sequence of this. It says the E varies directly as the cost of D. So thinking about how that would work with our setup, which normally says Y varies directly as X, now we have E varies directly as D. So that would be E equals our constant of variation K times D, our dollar amount. So you could use this direct variation setup to then answer this question. So it says if E equals 3.85 euros when D equals $5, find D when E equals 10 euros. So first, in order to use the direct variation function, we need to figure out what K is. So plugging in the numbers we know, I am going to have 3.85 equals K times 5. I divide by 5 here, and I get, let's see, oops, 0.77. So that means my equation is my euros is equal to 0.77 times the dollars. So I want to figure out what is the dollar amount when the euro amount is 10. So I'm going to take this number 10 here, plug it in for E, and I'm going to solve for my dollar amount. So I'm going to divide by 0.77. And we get the dollar amount to be 12.99 if we round to the nearest penny. So $12.99. Now, when you initially look at this problem, if you did not have this knowledge of direct variation, you could still solve this problem using your knowledge of proportions. And some of you might have thought to approach this problem that way as well, and that's perfectly okay because direct variation problems are proportional because there's that constant of variation that gets applied to our variable of our dollar amount here. So you could have used proportions as well if you wanted to, or you could have gone about it this way. In the end, though, regardless of what method you use to solve, you're still going to get $12.99 for our dollar amount when converting from euros to dollars.